Hello, my name is Tyler Ehrlich and I'm part of Group 3. Today I'll be talking about Part 1 of Project Number 4. Here we have the thermal expansion of stress equation, which is the change in temperature, which is 100 Celsius, times the Young's modulus, which is given, times the coefficient of thermal expansion. From there, we get 252 megapascals, which are negative in this case because it's compressing the bar because it's in between two rigid walls. That's for iron. For aluminum, we keep the same change in temperature times the Young's modulus times the coefficient of thermal expansion, which gives us in this case 158.7 megapascals. Still negative. The length of both bars will still remain 1 meter because the strain of it would remain 0 since it's in between the two rigid walls.
Hello, my name is Liam Mosier. I'll be talking about whether our data supports or does not support both the diffusion coefficient and the flux equation. Our data does support the flux equation because when we change our concentration, which is right here, our dC over dx, you can see that with a higher concentration, we have a higher flux. And with a lower concentration, we have a lower flux. What this means is that when we have more atoms on one side rather than the other, we would see a higher shift from those atoms on the more packed together side to the less packed the other side. And they go from high concentration to low concentration, eventually evening out with about an even concentration on each side. Additionally, our data supports the diffusion coefficient equation. Here, we have our diffusion coefficient is based on an initial diffusion coefficient times the exponent of the energy of diffusion times the Boltzmann constant over the Boltzmann constant times temperature. Here, we're looking for temperature dependence for our diffusion coefficient, which we did see. When we raised our temperature, we saw that we had a faster diffusion and flux. And when we lowered our temperature, we saw a much slower diffusion flux, much more potent than our concentration difference. For a diffusion coefficient equation, we have a diffusion coefficient is equal to dL times the exponential of negative the energy for diffusion over the Boltzmann constant times the temperature. This gives us only a dependence on temperature, as this relies on the material, and this also relies on the material. Boltzmann constant is constant for all materials, so our only change for the diffusion coefficient will be our temperature. And a small temperature will have a much greater effect. For our diffusion flux equation, we have our flux, which is equal to the negative diffusion coefficient times our concentration, which is dC over dx, which means our concentration over the length of time. So we'd have our concentration on one side over the minus the concentration on the other side over the total length. We have our initial conditions of 200 particles on one side and 0 on another. We also have our initial temperature of 300 degrees Kelvin on each side. Here, we're going to check for the flux of atoms. As you can see, relatively few atoms cross at first, however, more and more slowly go up, having a constant flux of atoms. Here, we lower our number of particles by 50, but we keep the same temperature. Here, we're expecting to find a slower flux of atoms, which we do, as fewer atoms cross the border per second compared to earlier, where more atoms cross the border. To prove our point further, we're lowering the number of atoms on the first side to 100 particles, but keeping the same temperature again to have a constant. Here, we can see an even slower flux of atoms, which proves that our flux equation requires a concentration to work. Now, we are going to prove their diffusion coefficient is reliant on temperature. So again, here is the baseline we had for our diffusion coefficient numbers at 300 degrees Kelvin. As you can see, a relatively stable flux that we saw earlier. The same amount, so no change noted. Here, we're going to lower our temperature by 150 degrees Kelvin. This is to show that we have a smaller diffusion coefficient with a lower temperature, and therefore, we're going to have a smaller diffusion flux. Here, as you can see, less atoms cross the border per second than earlier, meaning that the diffusion flux is smaller, and therefore, the diffusion coefficient is also smaller due to having a lower temperature. Here, we're going to lower the temperature all the way down to 50 degrees Kelvin. The reason we can't do it 0 degrees Kelvin is because absolute zero is not possible in the real world. And now, we're expecting a much slower diffusion coefficient, or a much smaller diffusion coefficient, sorry, and a much slower flux because of that. And as you can see, we do. We have a much slower diffusion flux due to having such a small temperature. Here, we are going to lower our temperature down to 50 degrees Kelvin and our number of particles down to 100. As you can guess, the flux here will be significantly slower. As you can see, the flux is significantly slower because the diffusion of particles is also significantly slower. This should prove without a doubt that our flux equation and our the diffusion coefficient are dependent on concentration and temperature each. Additionally, the way to show that our diffusion is much slower is because every single individual atom is much slower due to how low the temperature is. And because the concentration is much lower, individual atoms collide less, providing less kinetic energy to each other to launch them farther. So they usually stay in the same place overall. As you can see, with this kind of atom over here, there's no atoms near it, so it moves significantly slow, as no atoms give it energy. And even when it is hit, just like bang, it still stays slow, because atoms that hit it additionally are themselves slow as hell. For our very last example, we're going to show that when we lower the concentration even farther, and we keep that 50 degrees temperature, we can see that this is even slower of a flux. Therefore, proving again, without a doubt, our diffusion coefficient and flux equation are dependent on concentration and temperature. Here, you can see not even one has passed the barrier yet, as it requires the collisions to occur, which are very uncommon due to how few particles there are. Additionally, with our concentration, it's true that our concentration is actually a concentration gradient. So if we have more atoms on one side than we do the other, they will move from the larger side to the smaller side. This also works if we have atoms on each side at a ratio of 2 to 1, as we have 200 particles in the blue and 100 red particles here. As we remove the divider, we can see that most particles are moving to the concentration that's slower. However, there are also particles moving to a concentration that is higher, as this is diffusion, and does not just go from large to small. Some particles also go from the small area to the large area. However, most are going from large to small.
Hello, my name is Andrew Horn, and I'm also in Group 3, and I will be also presenting Part 2 of our project. Here we have a graph of the simulations we ran for diffusion. So this one right here, the dark blue line, is 200 atoms at 300 Kelvin. It has the highest rate of diffusion, as you can see, because it is significantly higher than the other lines, and that is because the amount of atoms is 200, which is the highest out of all of them, which increases the flux equation, and it also has the highest temperature, which increases the diffusion coefficient. The second line on here, the green one, is the second simulation we ran, which is 100 atoms at 300 Kelvin. At this temperature, equal to the first one, it still had a very high diffusion coefficient. However, for the flux equation, because its concentration was half that of the first simulation, it still diffused at a significantly lower rate. And at the end, it reached equilibrium and would have continued to stay at that line roughly forever. The third line on the graph here is 200 atoms at 50 Kelvin. Despite having the same amount of atoms as the first line, it diffuses even slower than the previous two lines. And this is because its temperature is massively lower than both of them. And because of that, despite having a high concentration difference, its diffusion coefficient is significantly lower, hampering its diffusion. However, it does end up overtaking the green line because that one plateaus at equilibrium.